Well, hi and welcome to my shop. Today I'm going to be resuming my tube experiments there you can see on my bench. So I've sort of pulled out the apparatus I was using in the last few videos that I was doing this work on. The whole situation had become much more complicated than I kind of anticipated. So I took a break, fixed the radio. Now I'm back at the tube testing test, if you like. And I've rearranged my equipment here to make things work better and make a little more simple to work with on my bench here, because things have just gotten so complicated. So my objective today with you is to kind of show you what I've done here. This is the same setup as the last video. If you've just finished the last video and you're starting this one, although a week has gone by and the equipment all looks different, it's really the same arrangement. So I'm going to run through it fairly quickly here. Then we're going to put a tube in. We're going to see if this thing works the way I think it does, because probably doesn't, and get all that sorted out so we can get right back to analyzing a tube like this. So this is the 6SN7 tube. It's a very good choice for doing this with, and I'll give you a little tour of my tube testing box here. Okay, so ignore everything on the top here except for the tube, the switch, and the socket. This and this, they don't mean anything. It just left on the chassis. Controls don't mean anything, but this switch means a lot. This switch is how I switch the B plus from either of the two plates. This is a two-part tube, so that's two plates, so I can switch the B plus, put it in the middle, and there's no B plus apply to either plate. Now internally what I've done is I've added a bunch of wires so that this socket over here, under here, is wired the same as this socket. They're just parallel. There's just 8 wires running between these two sockets. So I put a tube. I discovered after doing this, I can put the tube in here and put my tube extender socket here, which gives me all these terminals. I then got really clever here. And I put a diagram, or a chart, if you like, on the top here showing me what each terminal is. So I don't know if you can see that or not. My writing's not so great, but HH for the two heaters here. Then you have G1, P1, K1 for grid plate and cathode number 1, and then same thing over here, grid plate cathode number 2. So now, instead of me having to refer to the book every 10 seconds and remind myself what it is I can't keep in my head clearly, I can just look here. Fantastic. I have this wired up essentially the same as it was before. This is the positive voltage lead, which I want to put on the plate. P1, very good, Jim. There you are. Saved myself a minute right there. So this is energizing this meter, which we'll switch on now. Set them to 150. I have a couple scope leads hooked up here. We'll leave them on for now, but I'm not actually going to use the scope to start this up. So also the current flow on the plate is reflected in this meter here. It's a little hard to see, but you'll see. If you notice, I've labeled these plate. There's a label on here, plate. A label on here, load. So this meter is going to monitor the filament current, which, if you remember, was 600 milliamps for this tube. And this guy is measuring. And you see, I have filament up here and grid voltage here. This meter is going to measure the grid voltage. Let me, if I connect it right. This is not right here. This black thing I'm hooking up now is the cathode connection. I have to connect so many things to the cathode. It's kind of like a grounding point, if you want, or a neutral point, that I simply have an extender here so I have more copper to clip to. That's all that's going on there. We've left the 3 other plate, cathode, and heaters disconnected up here, but underneath the grids are connected directly and the cathodes are connected directly, but the plate is connected separately through this switch, through these wires. So I can select the plate that I want to energize, but the rest of the tube is operating regardless. I don't think that has any influence on anything, but I bring it up because, you know, this is a fairly experimental thing I'm doing here, and I can't be sure of anything. Nor should I be sure of anything. So first thing we're going to do is operate the tube. bring up its heater first, and then we'll start applying some DC voltages to the plate and whatnot, and we'll see what starts happening here. So if we want to heat up this guy, we should have this meter on. Okay, now way up high here, I might just use this other camera. This might work better. Yeah, let's try that. Just switch over. So way up high here is the power supply. Put it on standby. Have the oh, this isn't going to supply the heater anymore. It's this other supply. Right. Okay. Let me switch back to the other camera. It's just a little easier to see, I think. You see a little less of me too. So behind this clock, I will just slide out of the way for now. It's the power supply that's going to drive the heaters in the tube. DC power supply. I'm going to turn it down. I'm going to turn it on, and we should see a current right away. So I'm not quite sure why it was beeping like that. Yeah, not quite sure what was going on there. The power supply will beep if the load goes too high, and I think that's really what it's designed for. And a too high load on this guy is 25 continuous amps, so it's a long ways from there. So we want this to be at 0.6. Let's crank it up a little bit and get it up to 0.6. So I've been reading up on tubes, of course. All this stuff has sparked my interest, which is exactly why I'm doing all this. It sparks my interest, and then when I read things with interest, I absorb them a lot better. So very, there. That's good enough. That's pretty good. What I've learned is if you raise the temperature of a heater beyond its design value by just putting more current down it than it's really designed for, you can cause, I don't know what to call them now, chemical or metallurgical effects. Can drive off material from the surface of the cathode, like an off-gassing of materials into the tube. That's kind of okay as long as the getter is working well in the tube. The getter will keep absorbing these extra molecules. But I mean, if you look at this tube, and you see the spots on the top, and as I mentioned before, all these 6SN7s seem to have that. Let me grab another one. Okay, so I'm just grabbing this out of my bag of 6SN7s. And sorry about the focus thing there. Even if I just kind of rob the background from the camera. Well, you can see the two mirror-like surfaces on the top there. It's a little hard to show this in the camera, but right on the top are two little dots, that points where material has been coming up and hitting the glass. I think the other day I mentioned chimney effect. Well, I don't think there would be a chimney effect in an evacuated container, but something is going on causing the something to come up out of the inside of the tube here, inside of the plate, and form up here. So that's the deal. Don't overheat. That's why I'm saying this. There's some stories out there that if you have a tube that's weak, you can run the heater high for a while, and literally you're trying to drive off some contamination out of the cathode. Well, that stuff is going somewhere. So if the getter's good, it'll get it all. But if not, you start loading your tube with gas, basically. So I don't want to overheat those. I've got enough of them we can experiment around someday, but not right now. Look, it's settled right in perfectly at 600. Can't beat that. So next thing is, we start applying some DC voltages here. Now I do have a plate resistor in place. I can't recall the resistance of it, but I think it was 3K, 3 or 4K, somewhere around there. Something like that anyway. So there's some amount of plate resistance in there. This meter is reading plate volts. It's reading it right on the plate. It's not reading it from the supply. So the supply is going to go a lot higher than the actual plate voltage. plate current is going to appear in this meter. So I believe, let me set this here. So that's set to milliamps DC. I'm hoping in the long run this meter will be useful in, I can only get it to stand up nicely, maybe useful in reading the AC current flowing in the plate circuit. This is what my hope is. I think we're ready to put some DC voltage on there. And this meter is reading below 0 right now. Oh, we also need a C minus. C minus is very important. Okay, so C minus is coming up here on this meter. This is the grid voltage meter, grid V. So first thing we'll do is we'll make sure that this is at -8 before we apply any B plus to the tube. You gotta wonder when a radio is warming up, what's going on with the grid voltage and plate voltage, and are there times where the tube is really really giving a blast? And there probably is. There probably is a whole bunch of startup issues with tubes. All kinds of them, depending upon the circuit that they're in. Okay, so we're going to raise this up to -8 here. Uh-oh. Okay, so for some reason this meter's not showing it. Let's see if we can figure out why. It's just possible. In fact, oh, there's no plate voltage. That doesn't matter. That doesn't matter. We're looking at grid. It's probably the other grid that I'm energizing. No, both grids are getting energized. Both grids, Jim. So where's the grid voltage? It's not here. Let's see. Is it over here? The other grid show it? What's going on? Okay, we got a failure of the circuit here, which is just exactly what I was anticipating. Let's follow them down. Going in here and doubled over to here. I think that's quite correct. Is it somewhere unexpected? I'm looking for a -8 to show up. Maybe I wired it wrong? I don't think so. Now I can't check over here because I've got the tube extender here. Okay. I'm expected to do a little troubleshooting on this guy. Try as I may to get it all perfectly right. Need a meter that's a little more flexible. Let's start with this one. From the cathode to the grid. What did I see there at first? And from the other cathode to the other grid. Nobody's showing up. Okay, I'm going to kill the heater current. We don't need the heater flowing right now. I'm going to pull the tube out of here. Gotten a little hot. I'm going to measure right back in here. So cathode is pin number 3. 1, 2, 3, and the grid is right beside it. Nobody's home. Okay, going right back to here now. We have that cathode, we have that cathode wire and the grid. That looked pretty good. Let's try that again. Cathode wire and the grid. So there's our voltage sitting there. Why are you not making it in? It could be I had to rewire this. Looks like I clamped this down on the insulation, not on the wire. That's what it looks like. So we'll start with that. A little hard to believe the wire wouldn't make contact in here somewhere though. Okay, did that bring over the grid voltage here? We want to be on 3. And 1. There it is. Okay, so that's what it was. So I just had a bad connection. Bad connection. Okay, we'll pop this guy back in. We'll leave the heaters off for now, so the tube won't operate, but we can still set up all the voltages, or at least practice at setting up the voltages. So this is the grid monitoring voltmeter, and so it should be here. What happened? Shouldn't we see it here? No, not like that. Yeah, that's okay. What am I doing? I'm already getting confused by too many wires, and there isn't even too many on here yet. What happened? Three and 1. 3 and 1. Huh. Well, apparently I boobed up the wiring underneath here. How could I have done that? It's so simple. Nothing like a little troubleshooting in the morning. 1 and 3. I think that's 1. That's 3. Sure looks soldered over here. Hold still. Everybody hold still. So that wire's good. Now the other one is 1 and 3. What's going on? Did I just fix something? Just moving those wires a bit? Oh! Well, I don't know how many of you figured out what my mistake is here, but it's pretty hilarious. It really, really is hilarious. I'm now going to fix my mistake. So you can see I did not test this. I saved it for the video. Come on, man. There we are. I think we'll be better off now. If there's a way to get it wrong, I'm your man to find it. Grid. I guess these all remain correct. So we should, why are we not seeing it? Oh, I'm looking at the wrong meter, for God's sakes. I'm looking at this meter. Hey, you know, the man with too many watches doesn't even know which one to look at. Doesn't even know how many he has. That's how bad it is. Keeps finding watches. Well, okay. A little bit of trouble seeing all these meters. Oh, here we go. The sing-song has started. That's the control room telling me to hurry up on this. Okay, back on the plates. That's this guy here. Oh, maybe not. That guy. One of those guys. Okay. -8, we want -8 here. We'll raise this up to -8 fairly accurately. Okay, bingo. We'll put the current back into the filament here. Uh-oh. Oh, well, we need a tube in at this point. 1.6, about 2 amps there initially. See, it comes right back down to where it should. Not bad. Ready now for some, let's move this meter out of here. I'll start looking at it again. Ready now for B+. It should show up here. And some DC current, hopefully will show up there. If we put some B+ on it, I think we're ready. We'll aim for 150 volts to start. That's full scale on here. Just a second. Okay, should be showing. It's not showing. Okay, let's hold the fort. What is not right here now? So this switch is open. This is what's happening. I throw it one way, I energize one plate. I throw it the other, I energize the other plate. Don't know which one's which yet. Can figure that out fairly easily. The my panel here counts this way. So that's 1, 2. Oh no, it's the other way around. 1. How's this going to help me? I don't know which plate's being energized. Well, let's energize one of them anyway. So I have the voltmeter hooked up directly on here. So I would guess, because we've got about 75 volts available, we're not seeing it because it's the wrong plate. So I put it this way. There we go. Meter goes up. Excellent. So we want to raise the plate voltage to 150. Watching for current here. Current is showing 15 milliamps, 16 milliamps. Isn't that a little high? This is okay. This has gone just a touch low. 15 milliamps. 15 milliamps. Let's turn it down. I can't remember what the current is supposed to be. 15. So a 6SN7. 6SN7. I think I'm going to be raising the plate voltage a lot higher than 150. I've already got a pretty heavy plate current. Plate voltage 450 max. I'm not getting anywhere near there. Cathode current 20 milliamps max. Why do they call it cathode current as opposed to plate current? So one of the things I've done is I put this resistor into the plate circuit. I should probably put it into the cathode circuit. That might be a better place for it. Kind of amounts to the same thing. Plate voltage, it does two sets, 90 and 250. So 250 is where we're going to head. Grid voltage -8 at 250 plates. Plate resistance should measure out at 7700. Transconductance should measure out at 2600. Plate current 9. Yeah, see, that's very low. 9. Plate current for a voltage of -12 all the way down to 1.3. But I'm already... Hey, yeah, that's right. I cut this off, didn't I? Did I cut this off? I just turned it down until the current was nothing. I think that's what I did. Let's turn it back up. .26 milliamps. Maximum, let's read maximum plate current. See, all these things are taken care of with the tube tester. You don't have to sweat over them. 0.6, so I can damage the tube here while I'm trying to. Okay, which one of you guys is doing that? I will take the time to disable all the beepers in my meters at some point. Plate current, 10 milliamps, 9 milliamps. That's not the maximum circuit value when used as an oscillator. Just looking for anywhere where it says maximum. Sometimes I have a list of maximums right in the very start. Maximum ratings, plate cathode current, 20 milliamps max. So cathode current, plate current, same thing, pretty well. 20 milliamps, so we don't want this to go over 20 milliamps. It's already up to 15, 16 at a lower. So what's going wrong? Okay, who is it? Which one of you guys? This one. It was this guy all along. The difficulty here is it looks like the plate current is going to go out of control for some reason. Incorrect plate resistance. Really shouldn't matter. Kind of all this plate resistor is doing right now is dropping the voltage reaching the plate here, so I have to generate more with my power supply to get this 150 here. It's just dropping. It's just a waste. It's kind of a waste. Kind of a waste right now. What else could be throwing this guy off? I don't know. Let's get this back up to 0.6 here. Get this guy going again. Now, if I start rotating this switch, this is hooked up as an ammeter. I start rotating the switch, I'm going through ohms. Maybe I can just push one of these buttons and bring it back to life. Bingo. 10, you know what? This is 0.1 milliamps. That's what this is. Right, 0.1 milliamps. Okay, that's a little better. I was reading that as 10, but it's actually 0.1. You can't even see it on the camera. Okay. Now we're ready to raise the B+. It's almost at 150. Now I got the opposite problem. There's like apparently no current flowing. Let's take it right up to 150. Hope I'm reading that meter right. DC milliamps, it says on it. So that's 0.42 milliamps. Or is it 40 milliamps? Am I burning up this tube like crazy? I don't think it can be. So the supply voltage, according to my power supply, isn't much above 150. So conceivably not a lot of voltage dropping here. Plate current is right off. It should be in the range of 9 now, 9 milliamps, not 0.4. This is set 1 times this setting. The settings are pretty rough, but it's going to be somewhere around 3-5K. But because we're reading the voltage here, it doesn't really matter. I'm going around in circles now, aren't I? We're going around in circles. Bad tube. No. How can I get like a partial here too? Maybe this isn't correct. Maybe this just is not correct. Wow, how can it not be correct? It's not clamped on or anything like that. We'll have to try a different meter there, because we got to be sure about this. And maybe I'm reading it wrong or doing some other dumb thing. We'll try it with this one. Because we're working with current, I can't afford to make too many dumb mistakes here. So we're looking for current under 20 milliamps. So I'll set this on the 20 milliamp scale. Fortunately, I don't have to worry about directionality. That guy there. We'll break the current. Let the voltage relax a bit. That'll take milliamps. Common. 20 milliamp scale DC. Okay, let's try it again. I'm going to turn down the B+, turn it on. Raise the Titanic again. Tube's conceivably in cutoff. All the way up to here. Okay, I'm getting the same kind of reading now. 0.15 milliamps. Is it really 150 volts? Sure. 150 volts, sure. 150 volts up there too. We're up by like a factor of 10 here. Even more, a factor of 100. The current is 1/100th of what it should be. I have a scope connected here. I can't imagine it's affecting this, but let's take it off. Take this right off here. All the connections here are non-current carrying connections. These are all voltage test points, and, unless I do something stupid. So putting stuff on, taking stuff off shouldn't affect the operation of the tube at all. 0.21. .21. That's just, what is that? It's just a scope lead. What if I touch that with my finger? Yow! I am not reacting because of a shock. I'm reacting because of what happened over here. What does this meter actually mean here? If you can see it. It has a symbol on it. I've never actually really thought about this too much. I'll draw a picture of it here. So I get a piece of paper. Sometimes the things I don't know just stun me. The older I get, the more of that there is. So the symbol over here on the meter, yeah, is that. And down below it for AC, of course, is the AC thing. What is this? This dotted part is supposed to be telling me. Always appears on the volt reading. Same thing over here on this meter. So I've seen this, all these days I've seen this thing. I just pretend it's not there. Now I got to face up to it. What does it mean? Does it mean it's not reading pure DC? So when I touch the grid, I fire in a signal. The plate went down. Plate voltage went down from current flowing through the resistor, dropping the plate current. I'm basically feeding a signal into this tube. Now this meter's fooled because it can't separate the AC and the DC. And who is beeping at me? Are you? You're not even hooked up to anything. Get out of here. Well, I expected this to go a little smoother this morning. It was that guy, wasn't it? I did not change the wiring of this socket, this bar. Not on purpose, anyway. Let's see, I disconnected the wires there and reconnected them. I have a photograph of the wires. I better double check just to be sure. But so this red wire is carrying the B plus into the switch, and the switch is sending it on one of these two wires. In case you're wondering what's happening there. I am kind of stumped here. Wait a minute. Let's get this out of here. I want to get there. Get over there. Well, one thing we can do is we can jack the B plus up even higher and see if we can get this up into, maybe I'm just nowhere near where I need to be. I've got the grid bias set for a plate of 250, but I'm not at 250. I'm at 150. Let's push it. That's probably all it is, Jim. Let's just push it. And I might have trouble getting all the way up to 250. 250 would be straight up now on this meter. Going for 250. Now 1 milliamp. Look at that. Now it's cooking. Okay. So we take this up to, well, I want to stop around 10 milliamps or 250 volts, whichever appears first. Coming up on 250 volts. Just a bit more on the meter there. So that's about 250, 9 milliamps. -8, gone to sleep. Still have a 0.6. -8, just a touch high. Watch that current. I just lower this a touch. That's what this tube's all about, right? Tiny change in the grid voltage, big change in the plate current. Let's check against the book now, just to be sure of things. Right. Right, so don't be afraid to give it B plus, Jim. You're a chicken. I have a whole bunch of 6SN7s. I can afford to burn up quite a few. There are many, many 6SN7s floating around the world because they were used extensively in military applications and other things where they were used 5 and 10 at a time and stuff. So, we're looking at this. We're saying plate voltage 250. Yes. Grid voltage -8. Yes. Amplification factor, we don't know. Plate resistance, we don't know yet. Transconductance, we don't know yet. Plate current 9. Okay, so we're at 9.5. Plate current for a grid voltage of -12.5. 1.3 milliamps. Let's do that. Let's go to 12.5 on here. 12.5. What did it say at 1.8? Oh, it's not 1.8. .3. Ooh, it's way high. How come? What's up? Plate current for a grid voltage of -12.5. That's exactly 12.5. We still got 0.6 coming in here. Plate voltage running at, plate voltage gone up. Plate voltage went up. Plate voltage down, 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 because I cut the current flowing through the tube. Plate voltage down around 250. We're going to double check it because I'm using a meter whose precision is, whose accuracy is questionable. But now we're down to 1.3. We're right in the range. So let's count. As much as I calibrated these meters, they just can't compete with these fantastic digital meters. One of which I have. Oh, that's right, this guy. We want to switch back to the other meter because I need this meter. Okay, 1.3 milliamps. Okay, power off. Just the plate, the heater keeps going. Common out. Doesn't really matter. This meter's can go either direction. Okay, so this should read, what was it, 1.3, right? 1.3, power on. B plus coming back. 1.38, right on. Okay, that's really reassuring. That's really, say that there's so many things going on in here. My head's having a hard time keeping up with it all. And I'm painfully aware I'm shooting a video and I gotta keep things moving. I'm painfully aware of that, which is probably why sometimes you might see me act in a manner where you'd say, well, why didn't you take more time on that? It's because I'm painfully aware that people are watching. You are watching. Okay, it's not painful. Now what did I do this for? So we want to check the grid voltage. 12.5. Thank God I've got these super precise meters now. I mean, if I tried to do this 30 years ago with just a bunch of indicating meters, what a hopeless case that would be. At least I can rely on these. I'm sure they're accurate. Plate voltage is what I wanted to check here. So I better take this off current or we're going to have a surprise. I want to verify plate current. Plate voltage. Plate voltage can be found right here. What happened there? Oh, touching it today. Duh. Duh. Get back on the cathode now. Don't put it in the wrong spot. More plate voltage. I didn't have my meter set high enough. Once more. Cathode. Plate. 265. So we want this. We want this to be more accurate than that. $262. We want this to be right on 250 now. Two 250 is a really important number. So there's 250. Get back on there. Sneaker. So the big VTVM is showing 250. What I'm going to do, I'm going to cheat. I'm going to adjust the 0 and make this come up on 250 here. That's a poor way to calibrate a meter. So now when this thing says 250, it means 250. Great. Get this guy out of the way. What do we got now? So we're sure to have 250 here. We've got 0.6 there. We got the minus 12 and a half here. So we should be seeing over here 1.3, but we're not. We're seeing 0.9. 0.9, less than a milliamp. Now the thing is, this could be just on a knife's edge, in the sense that I adjust anything and we get a big jump into current here. So let's first try with the plate voltage. How sensitive is this to plate voltage change? So we'll go up a little bit. Look at that. But I went up 10 volts or something. I'll put this back on 250 exactly. Okay. Well, let's look at that. This time it's 1 point. It's getting closer. And plus, we're not testing an absolutely new tube. And you even have to ask yourself, as these tubes came out of the factory, were they that consistent? Were they really that consistent? I've been reading a lot on tube manufacturer and things like that. There's a heck of a lot that went into building these tubes. It's not easy. This is not an easy process by any means to build a tube like that. And all along the way, there are problems that could occur. So there's got to be an operating range, a plus and minus, when these things come out of the factory. As much as they don't want that to be the case. And the only way somebody out of the factory can sort all that out is to do this kind of test on their tube. Who's going to do that? So I think what we're seeing here now, because I'm just looking it over, everything is set the way it needs to be to generate the 1.3 here. We already know extreme sensitivity on the plate voltage, a few volts high or low, and this thing is totally different. I mean, the absolute precision on the voltages at the tube. You have heavy wires running between here and here, so it's just tiny currents to drive these meters. So these things are going to be accurate in what they read over here, even though the tube is there, in case you're wondering about voltage drops and stuff like that. So how could I resolve? Well, let's try this. We're in a position to know the plate resistance at this voltage right now. We can calculate that very easily and compare it to what it says in the book. I can't add, subtract, multiply, or divide, so that's a bit of a problem here. So if you take the plate voltage of 250 volts. And R equals E over I, so I just divide that by the current, and the current current is nicely 1 milliamp. Thank you, 1 milliamp. Does this make sense? So it's 250 over 1, it's 250K. Oh, come on. I'm doing something wrong here for sure. There's no way the plate resistance in there is like 7,000 or something, isn't it? 8,000. The tube, you shouldn't say plate resistance, you should kind of say the tube's resistance. The tube plate circuit, the tube cathode plate circuit resistance. Maybe the better way to put it. Where are we here? 6,700 or 7,700, depending upon the pressure you're putting on the tube. So did I do something dumb here? Yes, I'm sure I did. That's a dumb question. I've done something dumb. What is it? I don't know. Time for a break before I go any further, though, I think. The whole reason I'm willing to do this kind of stuff, aside from the point of ending up with a tube that I can use in other tube testers for verifying their quality, I could go through all this, is because look what it does. Look at this big book, and the front of it is full of technical information about tubes. And look where I am. I'm on basically page 1. Somehow here I am at the age I'm at, I can't get off page 1. Okay. Fascinated by the smallest things. So, can't do plate resistance with a static test. You have to make a dynamic test out of this. Let's wake these guys back up. Whoa. Took a break. So, what we want to do here is vary the plate. I'll read this again. You see, there's so many ways of making variations in the tubes that, oh my gosh, where am I here? I have to read this. Plate resistance of an electron tube is resistance of the path between the cathode and the plate. The flow of alternating current is the flow of alternating current. So that's the whole deal there. Plate resistance is a signal issue. It's the quotient of the small change in plate voltage divided by corresponding change in plate current. Plate voltage, plate current. Small change in plate voltage, plate current. That's what I wanted to find out. So we're going to do this at, well, we can do it here. I think we can do it at minus 12. I have 1.08, very, very stable current flowing there. Excuse me. Now trying to read the plate voltage change down to a fraction is going to require a better meter again. So clearly doing this precision stuff with older meters, not happening. Not really happening very well. Put that guy on. And then clip this guy on. So, well, we're going to clip the ground onto the cathode here. 3 cathode. Down here. Okay, and then the plates. And more accurate plate voltage reading got right here. 255. So we take, just writing it down here, 255 volts. And the current, hidden away there. Hard for you to see. It's right now, it's 0.99, so we'll call it exactly 1 milliamp. Now I'll make a small change in the plate voltage. We'll go up. We've got 5 volts. Okay, so there's 5 volts change, a delta of 5 volts. And we now have a current of 1.17 milliamps. So that's a change of 0.17 milliamps. So 5 volts yields 0.17 milliamps. So R equals E over I. We just divide that out. Did I keep my calculator in here? What have I done with it? Oh, I did. Great. I don't have to think. I don't want to think. E over R, so a change of 5 volts caused a change of 0.17 milliamps. 29 times 1,000. 29,000? And what are we actually expecting here? We're not expecting anywhere near that. So I was all happy I wouldn't have to open this book repeatedly while I'm doing this, but that's not what's happening. 6SN7. 6S7. So plate resistance at 250 should be 7,700. I got 30,000. What am I doing wrong here? Maybe I advanced this too far. What if we just did 1 volt here? I think the delta is supposed to be very, very small. Let's go back to, well, let's do this all over again. Let's start at 250. We'll do it with completely different numbers here. 250. Okay, 250. I'm getting a 0.86. 250 gives you 0.86 milliamp. Oh my gosh, that's way too low, isn't it? I'm way down. I'm way down in the curve. Let's change this to 0.8. I think this is a mistake. 0.8. Watch the current go up. Watching the current go up. Making sure it doesn't go over 10. See, the plate voltage has gone down because there's more current flowing. A little further, a little further. Okay, let's leave it this a little high. We'll raise the plate voltage back up to 250. So how do we get a little high on this? Maybe the house, the hydro voltage is going up a bit too. We'll get this right to 0.8 now. So watching the current. Current's at 6.8. 7. That's okay. So here we are at 8. We're at -8. So we're at the place. We're at the place. -8. 600. 250. What do we got? 7.46. So now 7.46. Okay, so now we change the voltage. It's not quite 250, is it? Okay, so we go up from here, say 5 volts, we'll go up to 253. Why not? Let's go to 253. We'll go 5 volts on this. 253. Okay. 253, and now we got 8.08. So delta 5 volts. It gives me 8.09, and the change in the current is actually, I'm going to use my calculator. Is 8.09 minus 7.46. 7.46 equals, I better get good at this because I'm doing my taxes later today, finishing them off, so better learn to add and subtract. So we get 0.63. So a change of 5 volts yields 0.63 milliamps. 13, 886, 253. Got 814 there now instead of this. So this number's gone up a little bit. So let's make it 0.65. A little easier maybe for calculating. 5 volts. So again, we do the R equals E over I. So 5 divided by 0.65 M milli. 5 divided by 0.65 times 1,000, just to get the whole number up here. This yields 7,692 ohms. Plate resistance 7,692. Now here's the problem. This is very close to the correct answer. We're matching the book. Very close. Oh my gosh, it's really close. I got 7692 and the book says 7700. The fact that the number in the book is written to the 100th, 7700, it's not 7702, means they don't even put these numbers in here with any kind of precision. So 7700 plus or minus 100. Bingo! Bingo, I think. Okay, I think I have this. I think I got a hard enough grip on all this stuff now. We can actually analyze this tube properly, do all the studies. I hope to generate characteristic curves, the whole shot on this tube, and really burn out the last of my brain cells on this project here. So thanks a lot for watching. I hope you're getting something out of this. I know it's a little confusing watching me. It's confusing watching a confused person, but I think we're getting there. Pretty excited, actually. Thanks again for watching.